Three women, three situations, same condition. These two will be called super women over time, and the last one won't survive. What I'm talking about is hypoxia. We know this. We have ran and we have felt our muscles sore and tight. That's hypoxia in the muscle. So what I'm talking to you today about hypoxia, I have no answers to provide, but preliminary results saying, hey, sensor world, wake up. This is a real problem. Every one of the speakers before me brushed what I'm going to talk about under the rug because it's a hard problem. Okay? So I am Shree. I'm here. I work in Tyndall National Institute, and this work is thanks to the help of all of these people who have given me the technologies available around and given enough bandwidth to make this question become real. So thanks to the speaker before, you have heard of the near-infrared spectroscopy already. You have heard till 1700 nanometer that all solutions are possible. And I'm going to talk about the bigger problem, which is after. To understand what the problem is and why sensors need to wake up to this, I'm going to go through where the unmet need is, where it is in the clinic, and then talk about where we are and why this is a possible solution today, but still not there yet. Okay? So, right. Okay. When we are talking about hypoxia, basically we are talking about oxygen, which is transported through blood. We know we breathe oxygen, goes to our lungs, goes to different parts of our body. Different parts of our body, if you actually measure the oxygen content, is not uniform. We are very, very diverse tissue having people. Okay? So brain is something that uses a lot of oxygen because it's running like a 40-watt bulb all the time. And the other organs, especially the skin, doesn't use as much. Having gone through this, when the oxygen drops, that's not enough to call it hypoxia. What you need is a physiological reaction. That is, your body needs to switch gear from normally taking in oxygen, taking the glucose and producing what we breathe out, which is carbon dioxide and water, to switching it to a lower energy producing regime. Where what I'm talking about is the hypoxia that affects us normally physiologically. If you go back and read about hypoxia literature, which won Nobel Prize in Physiology in 2019, you will see the role of it in actually heart attacks, cancers, and every single place possible. So the two women, one in Tibet and the Japanese women swimming underwater, for both of them, over the years, over generations, their blood vessels adapt, their number of red blood cells adapt to process low oxygen environments, whereas in cancers and everywhere else, you can also see that the whole body reconfigures in such a way that oxygen lack is adapted to and may cause disease or make you superhuman, both ways. Okay? Now, the most basic, if you've ever taken some biology or even you've heard of this, you know, I just said you produce carbon dioxide and you produce water. So this is the cycle I'm talking about. Your blood is going to transport oxygen into any cell in your body and takes up glucose and goes through this cycle where the oxygen is going to get used up in mitochondria, produce these lovely energy molecules we all love, and then you have the carbon dioxide coming out, and then you have the hydrogen ions coming. No, you don't have this now, but yeah, you do have this. So basically, oxygen, carbon dioxide, and water is formed here. Okay? Next, what happens? This is where the magic is happening. This is where the oxygen is going. So what's going to happen when I drop the oxygen? When I drop the oxygen, this path gets shunted to making lactate, and lactate comes out. Then you also have this shunted path giving you H plus ions. That's acidity. And the acidity is going to drop. And you can see these two are not happening at the same time. They are gated separately. So our body is very, very complex. Okay? And this is, as an electrical engineering, this is the best understanding I can give you. Now, let me take you to a real clinical situation which started this as a very interesting problem for me. What happens is, during labor, in a clinic today, these are the typical sensors that the doctors have access to. Look at these. You have a constriction sensor, great. You have a hydration sensor, measures water. Obviously, you can now use a smartwatch and a phone here, but that's not what's used in clinic. You can measure the heart rate, you can measure blood flow, temperature. These look fine. SpO2. Thanks to COVID, we now know you clip on a nice little photonic sensor and we measure SpO2. A lot of people are going to tell you it doesn't work if you are not white. If you are a child, it definitely doesn't work, okay? By child, I mean under 1 week of age, by the way. And here, these three. You see lactate, base deficit, see it as HCO3 and pH. These are the three things that are coming through that are actually relevant to actually measuring hypoxia. Guess which one has a sensor and the others don't. You'll read a lot of literature. We've already seen some people show sugars and lactates through the morning, that there are optical sensors for it. Then SpO2 we know. pH, there are optical sensors. There is also some for base deficit, probably not. But what's the problem? Why am I highlighting this as a big problem today? Because even today, this is the chart of what happens in the clinic. They say, okay, there is pH is between this, lactate has gone up. But to even get this chart, blood has to be drawn. That's the only way available. All the sensors require blood, okay? So now what I'm asking is, how do you make a non-invasive pH sensor? Let's take the hardest problem one. Lactate sensor, we have some answers. How do you do a non-invasive pH sensor? pH. pH is a fun problem. The level of pH in blood is a small, narrow range. You go out between 7.2 to 7.4, I think that's where we are as adults. So the minute you're out of it, you are acidic. You have ketosis and so many things. Your kidney is bad and da-da-da. But pH has different values depending on which part of the body you go to, okay? And this is where the fun part is. If you make a pH sensor, you will probably get a Nobel Prize if it's not invasive. These are the common sensors today. The classic one, pH strip, maybe a lot of us have seen this in chemistry labs in school. They have made fancier ones. We saw in the talk yesterday, calorimetric and adding photonics there, making the reaction happen, and then keep on going that way, make it optical. But in everything, the H+ ions have to react. You can go make it really fancy. This is how the detectors work now. You have a glass bulb that actually induces a voltage into the glass bulb, and it's still a reaction. You still need to stay in touch with the samples. You can make it really fancy, go to microneedles. Now I introduce the problem to you. Microneedles would have been great. At least, okay, you can say that's what it works. But I showed you how pH varies in every single part of your body. Your sweat pH is not your blood pH. Your blood pH under the skin is not your systemic pH. When your blood is drawn, it's drawn from the circulating blood. What's under your skin is just the blood that is pooled under your skin. So this is the problem. What we want, minimum, is to go into capillary bed. How do you go into capillary bed? We have heard about near infrared. You can go into capillary bed. In fact, there is a lot of, you must have seen, I asked the question today morning to him, asking what's the technology you want to see? And he said, I want to see, instead of doing the positron tomography, we use light. That works sort of for small brains, I mean small sizes. Because you can use 690 and oxygenation hemoglobin wavelengths to do this. But what doesn't work is you can't measure lactate or pH in these. Why can't you do that? There is a whole field of wow, my words have disappeared. Aquaphotomics, thank God we have words here. aquaphotomics that is looking into different bands of how water is changing with salts and pH and all, and trying to map it to spectroscopy. But pH is hard. Why? Because you're looking at two different water bands where the absorption is about 30 centimeter inverse. That is 1 by E attenuation by the time you reach 1 centimeter in 30 centimeters inverse, and the other one is 100 centimeter inverse. That is within 1 by 100 centimeters, it's 1 by E attenuation. So this band is 30 centimeter inverse. This band is 100 centimeter inverse absorption peak. When you listen to any speaker, they avoid these bands when they're talking about this. And this is where water has a signature when pH changes. Luckily, if you're measuring in human body and you don't have fever, you get your own thermostat. That's one problem solved. So why hasn't it worked yet? Absorption. This is a reflectance geometry. It's not even reflectance. If I just take light, put it on skin, this is Monte Carlo photon distribution at these wavelengths close to this. And you can see you have some luck with the 1470 band. You can reach about half a centimeter inside. I'm talking reaching about 2 millimeters. So if you use reflectance, you'll get some light back in the first band. In the second band, no. But what you can do is you take the loss, you generate local heat, and have powerful sources. So this is what is happening now. We are talking about two bands here, which are sort of not discussed when you're even looking at how do you, what windows are opening up in spectroscopy. Two technologies have driven a lot of optical communication and sped that up. One is to make devices faster. So you have 3-5 material world that has exploded to make device smaller and faster, which means because they have engineered band gaps, now you can also engineer them in these and create more powerful sources. The other one is fiber optics, we have heard has gone from telecom erbium sources to having thulium, polonium, so you have more sources now. So you have more and more sources coming up. So this is where Brian and Fatima came in. Brian is an expert in 3.5 and Fatima is great with fibers. So we're like, you know what, let's see how deep we go. And this project is just that. If I have, this is the standard tungsten halogen lamp, which is as good as, I call my glorified Christmas light because it's yay big. And we got it as a free sample from one of the companies. We said, look, we need NIR sources, and they're like, take it for free. So we got it as a free source here, and this is what is used in a lot of long bench spectrometers because it emits everywhere. And then we went with semiconductor diode from Thor Labs. This is one of Fatima's sources. We got some lasers because I love lasers. I have a laser background. I'm like, I'm going to stick laser everywhere. So we have these categories, and let's see what they do. So this was the simple setup. Put any source, vary the pH, collect true optical spectrum, not the interferometry one, because I wanted true powers to see how bad we were doing. And this is what happens with semiconductor diode. You see an absorbance like this. Okay, for 1470 band, almost everything works, no problem. But it's the 1900 band, everything starts to wiggle around 10 dB, but actually the absorption is nearly 50 dB there, and the only thing that goes through is the laser. So answer is, of course, lasers. But also what happens is if you use lasers every single time, because you have more photons interacting with the sample, your sensitivity sort of increases. So this is where we are at. At this point, I'm going to tell you that the spectroscopy, the way we do it, is not good for this. And that has to change. And that's where I'm at. I'm looking back and saying, hey, yes, lasers. But the spectroscopy is the problem. Just the absorbance spectroscopy will not do for this problem. And I had written a grant. I won it. I'm going to start that project in September. And this is basically the preliminary data that led to that grant. And I'll be having a PhD student to struggle with me in figuring out how to this. Actually, it's a lot of fun, but yeah. So that's what we are going to do next to measure pH. This is second part of the work I usually do. The other part I do is detect lactate in the bands that Mary was talking earlier. But I'm looking at 2 micron to 2.5 micron, where the information is really, really rich and the sources are poor. And it's called, I call it, we don't want to make photonics here because nobody needs it window. Because the photonics can be pushed, but they don't want to push it because there is no real use case. So we'll push it if we show that we can do some measurement of lactate or glucose, other than having all of diabetes market in our pocket. We'll also probably push the photonics to do it. So for those of you who are interested, glucose monitors on watch have sort of been coming around. Rockley is a company which sort of developed that a while back. Hasn't come into market, sold it to Google. Don't know where it is yet, but we should see it soon. So that's my 20 minutes. I do have all of my team to thank. We are a 40 plus people in biophotonics group, and I have a plug-in. There is the Gordon conference in US next year. If you are doing anything with optics and medicine or biology, please reach out. It'll be a fun conference. I'm chairing the one with the early career and students. We are talking about how to push light and push life. So both of these. And of course, a shout out to our sensor cluster.
Okay, thank you very much. So we have time for questions. Is there any question from the audience? Okay, Anna?
The idea of multiplexing the laser is very nice. We have given something multiplexing LEDs.
Yeah.
It is different. But in that case, you do not use a spectrometer. You just use a detector, right?
At this moment, we are using the optical spectrometer, but that's mostly to see the performance. You could use a spectrometer, but then you need to switch the light, like, you know, yeah. Can you do it continuously? You could actually.
Multiplexing with, you have line multiplexing sequentially. You shine one at a time.
No, you could, because it's a spectrometer, it normally is going to divide your spectrum into the lines, except, yeah.
Okay.
So that should be okay. That's, I think, like, you know, when you do for measuring SpO2, like when you're measuring blood, you typically use 2-3 lasers. If you want to use lasers, you can use 2 or 3 lasers. You don't need to, if you're using a spectrometer, you don't need to separate them because the spectrometer does it for you.
The simple detector.
Simple detector.
You switch from one at a time.
Yeah.
You get the same result with cheaper.
Yeah, I agree with you. That's my approach, saying use 10 lasers, but switch them on one at a time.
Spectroscopists at the moment are trying to move the detection part to the
Source.
illumination part.
Yeah, I agree. That's easier because you don't have to compromise on designing for power or designing for, it's slow now, but, you know, like you can use less power in general, yeah.
Okay, thank you very much, Shree. So let's thank.